Should we start recording? No. Okay, sorry. Okay, thank you for attending this update of the build called AFW Flex Wanderer. So my name is Eric, and I'm going to talk about what has been done since our last presentation, which was in August this year. So this build is focused more on the, let's say, the software part of a Mars rover, okay, where the focus of the software is to try to have more autonomy. So I will talk about what autonomy means here later. Okay. And so the basic idea is to use an existing hardware so that we can send a picture, which looks like a spider, and try to make it more autonomous. And so here it's autonomous in the sense that we are trying to be a wanderer. Okay, so it's about navigation and roving and discovering and mapping and things like that. Okay? In the name there is the word flex. Okay, the reason for flex is that it's what we're looking for in autonomy. Okay, it's the capability to deal in a more flexible way with navigation. I will give an example of that later. And the last point of in the name is the AFW. So AFW, the A in Greek is the negation. Okay, so it's to point out that there is a lot of inspiration from biological organisms, yeah, but it's definitely a robot. Okay. So the concrete goals of this work is to write software, but the software that is adapting to the situation. Okay, so while navigating is to adapting of what can happen while we are navigating. In concrete terms, we target this project to run on a fully fledged computers. Okay, so typically Raspberry Pi and such kind of SBCs. But also later, I hope this work can evolve to work on microcontrollers as well. Okay. It's a software, and in the robotic world, such kind of software is often seen as a middleware. Okay, whatever that means. Okay, but the thing that we are also considering, we have reasons to think that maybe we need to go deeper and to have actually an operating system. Yeah. So it gives some exciting perspective to such kind of projects. Okay. A short word on what adapting means. Okay. In terms of software, it doesn't mean the software is portable in a traditional way. Okay. I will talk about that later. Okay. It's the software is really adapting to situations. Okay. And that's an important distinction that I will detail later. And this project is started in January this year. And the roadmap has been as follows: that first was to build a test bed. Okay? So it's to take one of those spiders and to be able to work on the spider remotely, to upgrade the software, change the software, remote control, and experiment remotely on this hardware platform. Okay? And this test bed is a foundation to work on ideas around autonomy. And the test bed exists and it works for many months, and other people, including Mayer, have contributed to it and made it much better. The second point in the roadmap was to use this test bed to work on the software stack. Okay, so this is a thing that looks like middleware and operating system. And so this is about providing tools, so software APIs, to be able to work with ideas around autonomy. And the last point is the actual autonomous features for the rover. And the name is called a BOSS. Okay? So the name BOSS, there is OS in it. Okay? And it's a play on the word that is in the history of this project. We'll come back to that at some point, perhaps. But about BOSS, so the idea is this stack that I'm trying to show since the beginning of the project, okay, which is kind of showing the intention, okay. And so we can see we assume the gray parts. We assume we have a hardware and a typical operating system, okay? And on top of that, we build the middleware. And this stack uses names like System 1 API and System 2 API to map to recent, how to say, concepts that became a kind of mainstream, okay, from psychology. Okay, but the thing that I'm renaming that right away for a couple of reasons. Okay, and so the System 1 becomes a reactive API, and the System 2 becomes a deliberative API. So it's a bit borderline why I do that here today. Just that for consistency, I just claim that I do the change, and I will explain that step by step. But there is a background to avoid misunderstanding because of what System 1 and System 2 actually mean now in the mainstream. Anyway, at proposing step by step along this project. And so how it is today is like you can see on the right stack. Okay? So at the very bottom, you have this I wonder spider-like boat, on top of which we are using Raspbian operating system, which is the standard one for Raspberry Pis, and the custom software that we have. And so what I've talked about on this project so far and going to talk about today are part of these colored stacks on the right. Just the last word on this is that the way this project goes forward is not to work on each layer in turn. Okay, this is one approach, and in fact, several projects in the past, in the 90s and so on, had such kind of approach. But here, it's more about working on verticals. Okay, so it's across the layers. So here, this graph shows the guideline for this project, where it's going, but how the work actually happens is more in terms of slices of work along that. And the reason for that is because this project is very data-driven, and I hope you will see that in the rest of this presentation. Okay, so I talked about autonomy. Okay, autonomy can mean a lot of things, and a definition I like, if I can put it correctly, okay, is it's the ability to not react immediately, basically. Okay, it's so for a robot, it's the ability to plan ahead and to act on these plans. Okay? And so a very simple scenario will focus on navigation because it's something essential to rovers. Okay? It's also because we can see also already plenty to do there in terms of autonomy. Okay? And so very simple scenario is the image you have here. Okay? That we have a rover that is in A, and the goal is to go to B. Okay? And so traditional robots, they will have what is called a plan. And so a plan is, for example, a route to go from A to B, as we can see the line here. And this line goes through an environment. And for robots, it's a real environment with real objects and so on. So for example, rocks. And so on. So here, the rocks are clearly not on the path, okay? But we'll see what happens if it does. So here we have the starting point where we have our mass rover in A and has a plan to go to B, okay? The thing that happens very often is that sensors who perceive the environment have some accuracy. Okay, and when we're talking about space, even very high accuracy can be still limited. Okay, and so from Earth we can tell our rover, okay, you can go from A to B following that path because we measure that the rock is not in the way. But when the rover actually executes the plan, it's possible that we made some error on the placement of the rocks, and these rocks are actually on the way. Okay? It's also possible that the rover is following some kind of positioning system. Okay, and this positioning system is has some issues. Okay, okay, and so what we would expect is that for such a rover to say, okay, well, I will just go around this rock. Okay, and so that's very simple for us to come up with this idea. But in fact, we know it's extremely hard for robots to come up with these ideas. In general, they don't do it. Okay, we see some robots like Boston Dynamics, dogs, and so on, with similar abilities, but it's not clear how much they do that by themselves because um, the robots that are deployed are very often remote controlled. Okay, so it's not clear when the remote control is active and when the robot is actually reacting by itself. Okay, so this is a kind of a very simple scenario, and so simple that we may think that it's not a problem, but actually it is. Okay? And so one of the reasons why this happens in robots and rovers is that basically what they're doing, the planning, all the software is hard coded, okay, and it lacks flexibility. Okay? So the history of planning algorithms for robots is pretty long, and they are very powerful. They are flexible. Okay? But the thing is that they have some limitations, okay, at different levels. Okay? And so the limitations are one thing, but there is something else also, is that they are closed forms. Okay, closed forms means here they won't change. Okay, they are handmade. Okay? So they are designed by very clever engineers. But in a way, these algorithms are as clever as the engineers, basically. So if the rover faces a scenario that it doesn't know, or that was not um, conceived by the designers in the first place, standard engineering practices is to say, okay, we fail safe. Okay, we just don't move. In a good case, okay. Sometimes it can break the robot, basically. And so planning algorithms are also dynamic, so they're handmade and they're complex, and they're getting even more and more complex. Okay, but also planning algorithms are fixed. Okay, so this is the opposite to flexible. Okay, um, fixed in the sense uh, in many senses. Okay, is that quite often they are deterministic. Okay, and so the thing that determinism is a property we want in terms of safety for the system. Okay? But in practice, when the rover has a camera and is able to identify what a rock is, okay? All rocks are not alike. Okay, and so it's possible that a rock is misinterpreted for just a background or some noise or whatever. Okay, and the fixed algorithm we is as good as what the perception will be able to do. Okay, and so talking about perception, recently we had the deep learning revolution, okay, which has made perception and perception in robotics included much better. Okay, but this also it's very flexible at training time. Okay, that if you have good data to say to show what a rock is and to train a deep learning algorithm to learn what a rock is, we still have limitations. Okay, because it's as good as the diversity of the data you have provided to the algorithm. Okay? So deep learning is really state of the art in computer vision, in sound analysis, and so on. But it's not broad, okay? And this is a big discussion these days about the relationship between deep learning and AI. Okay? If we talk about AI as something very flexible, very human-like in a way, deep learning is a very powerful tool, but it's not enough in the sense that it's not broad enough. When we do deep learning, it's for one task, it's for finding rocks, for example. But the deep learning algorithm we get to finding rocks will be pretty useless to find something else, like let's say a cat, for example. And so there is also something very that we miss a lot, is that often we think that deep learning is dynamic. Okay. But in fact, no, deep learning is also fixed. Okay, what is dynamic in deep learning is the learning parts. Okay, so while we are not using, while we are making our algorithm, we feed data into it and we make it learn patterns. Okay, so for example, finding rocks. But once we have something that is good enough, okay, so it means we have usually a high accuracy and such kind of measures, we freeze it. And this frozen algorithm is put on the robot. Okay? But at this point, it's frozen. Okay? I am not aware about a significant experiment where deep learning is continuously updated on the robots. Okay? But the deep network that has been deployed on the robot is updated by deep learning. Okay, this is very rare. It's recently it has been called continuous learning, okay? And it's very rare. But actually, there is a lot of impedance for that. Again, because of safety reasons when we're making a robot. Okay? Because I don't know whether you've seen, the robot arms working in manufacturing, for example. These robots weigh hundreds of kilos, so you can convert into pounds if you see what I mean. I think that if one of those robots hits you, sorry, but I think we won't be talking again anymore. Okay, the these robots must be safe to use. Okay, and so safety means a lot of things. Usually, we have an area around those robots where humans are not supposed to enter. Okay, if you enter, then it's at your own risk. Okay? But also, we want the movement of these robot arms to follow more human patterns. Okay, because sometimes you can see robots when they need to go from a point A to a point B, they will take a very strange trajectory. Okay, that can be very surprising if we don't know about how these things work. Okay, a human would just go from A to B in a straight line, basically. But the robots, because of some constraints on their servos and their physics, basically, they have to take a different way. And it turns out that some robots trained with deep learning um, can take a um, very strange, um, very strange trajectories. Okay, so these are about autonomy in the case of robots. Okay, but after there are some known limitations from broader AI concepts. Okay, so by broader AI, I mean what is now called a GoFi, so good old-fashioned AI. Okay, which is more about symbols and so on. Okay. And so these studies are a bit, to some extent, out of fashion now because of the era of deep learning. But still, there is a lot to learn from them. Okay? And so, what we learn from, let's say, old school AI, okay, is that something that is really lacking, and that's something that deep learning is, for many reasons, there are very strong arguments to say that it's not possible. It's creative reasoning. Okay. And so you see the scenario of going around a rock because it's in the way, okay? That can cause some level of creative reasoning. Okay? So it's a very simple scenario. I admit it, okay? But it's still, at the core, it's a very similar mechanism. And so also from old-style AI, there are mechanisms that we know and that are not used in AI systems of today. Things like abductive reasoning. Okay. So that was the topic of our previous presentation in August, and I refer you to this to that presentation for more detail about the background. But again, with abductive reasoning, we hope to introduce some level of creative reasoning, let's say. Okay. I will say that it's not enough, but some more flexibility. Okay? And as we're talking about engineering robots, again, there are some issues of safeties and so on that come into play. Okay. So put all together with the background and the motivating scenario of going from A to B around a rock automatically, the idea behind this build is to really be data driven. Okay. And so it's to really use data, raw data, to in a different way of what is done with the traditional system programming, including robots. Okay. And so this picture can be scary to see, and it's complex, and I'm going to explain it, but it's really the core of of what this project is about. Okay, so all that is going to be in software, and this is about explaining it. But in fact, this representation is actually simpler than what it really means, which is the next slide. Okay, sorry, how did it work? Yeah, okay. So here, the difference with the previous picture is that I removed all the wording, okay, to emphasize that the idea is really to work with data from beginning to the end, all across the system. Okay? So this is a bit an extreme view, but it's to illustrate it, is that in a way, a robot doesn't need to be able to explain with the words what it does. Okay, a robot needs to do that so that we can interact with it. Okay, and so I will use words, but something you have to understand is that behind these words actually are data points. Okay, and so that can be a bit hard to understand. So that's why I'm using words, and that also helps me present and helps me reason about it as well. Okay. Anyway, let's get started. So at the beginning, you see on the left in the area where you have the plots. Okay, these are raw sensor data time series. Okay, so we have, for example, a servo on the rover. We have maybe a temperature sensor. We may have also a position sensor that sends the signal. Okay, and the thing that we in this project we take all that raw data, okay, and we turn it into something we can see in the video. Okay, each data point is actually a representation of the data over time. Okay, and as you can see, as you can see, there are clumps of data. Okay, so that we call clusters, and that way I will also call concepts. Okay, so the idea is that the robot has many sensors. Okay, and so from these sensors, it perceived the data. Okay, and so this data is about the time series. Is a time series about the readings of everything that happens to the robot. Okay, so it can be quite numerous. For example, in the case of our spider boat, we have 18 servos just for the legs, plus servos for the head, and after we have other sensors. We have a camera, and we have a temperature. We have internal voltage and things like that. Okay? And so the idea here is that everything is fed into the computer of that robot, and the computer uses this time series data to create a cloud of data. So I will explain more about that with the demo just after. But the motivation to do that is, you see, as we represent it in some space, okay, we can see there are clusters, and clusters are stable. That's why I call them concepts. Okay, that even as data comes in, so new clusters can happen, can be created dynamically. Okay, but the thing that some clusters get stable. So we don't know which cluster, what each cluster means, but we see they are stable. There is stability in the cloud of a data point that come from the sensors. And these stable clouds are what I call concepts here. And so let me do a quick demo of how it's done here. Okay. So the demo can be relatively long, but you have the link to this. You can access it. You can try it. Okay. And I try to put some explanation on how to adapt it. Okay. I won't run it because it's a bit long to set up. Okay, but it's all ready. Okay. So what we do here is that this is a program, okay, that loads up sensor data. Okay, and so the sensor data come from the spider boat of Meyer. And so we try to have simple scenarios for going from A to B and collect data for that. Okay? And so I just load the data, and once it's loaded, you see it's a section of table where we have, so the P1, we have 18 servos, okay? So P1 means the position of servo 1. Okay? For these servos, we can have the absolute position. T, the temperature, V is the velocity. Okay? But here we for this presentation, I will just use the position. And so here you see if we plot this data over time, okay, it's pretty, how to say, there is a lot of data, okay, so that can be pretty confusing. But this is just the reading of the position of each sensor, each of the 18 sensors over time. Okay? And I don't know whether you see patterns, okay? But the thing that you see, there is some things repeating, coming over again and again, okay? And so this is the basic idea is that are those patterns really there, okay? And so we can use data analytics, including machine learning, to try to show these patterns and perhaps get the clusters. And this is what I showed earlier. So here I'm representing the same data, but normalized, okay? This is just a trick a trick and sometimes necessary to stabilize what the thing does, okay? But I will pass on the detail, but there is a bit of machine learning. Everything is in, and if you have questions later, I will be happy to explain. And the thing is here is that the result is generated here. Okay, so please do not mind too much what's happening on the screen right now. Okay, because it has not converged yet. Okay? The algorithm I'm using at the end to try to find the clusters is this one has to be learned, and this tool doesn't allow to save the result. Oh, I didn't find how to save the result. Okay. The thing that you see as it's learning out of the data, trying to see whether there are some patterns in it. Perhaps you see that step by step we can see clusters forming. Okay. So it can take some time. Usually around iteration 800, we start having a stability. So we are approaching. So the algorithm to generate data is not very mysterious, but it's pretty clever. Okay. It can also be very hard to interpret. Okay, so and I'm still working on the interpretation part. Okay, so you see in this. Oh, by the way, in this work, I represent the data in 3 dimensions, but it doesn't have to be. Yeah? So as you can see, some clusters start appearing. Okay, and we are past iteration 1000 now, but you see it's moving less and less. It's getting more and more stable. Okay. So interestingly, there are clusters, but you also have points between the clusters. Okay. And so this is work I still have to do is to understand what those points mean and whether they have a meaning at all. Okay. But we can see the stability of the signal. Okay. So back to the presentation. So we are here where we start having these clumps of data points that become concepts. Okay. And so the next point from that okay, is to find labels. Okay? And so I put labels in text here for presenting, but please keep in mind that the robot doesn't need those labels. Okay, it could call it label 1, label 2, label 3. It doesn't matter for it. Okay, it will matter for us to have a semantic, and this is where we have discussions about AI ethics and so on. Okay, anyway, here I just put label. Okay, and so this clump of data. Sorry, something's broken in my presentation flow. Okay, so sorry. The blank part here should be this video about how the data points are clustered. Okay, but what was missing is this part. Okay, is that I mentioned about sensor data coming in, and the robot can make its own clusters, its own concepts out of that data. But there is another input usually. This is by definition a robot, which robot means slave. Okay, is that we also have a command. So here, for example, is a goal. Okay, and the goal is also a signal we send. For example, go to A. But go to A is also a signal that is digitized by the robot. So it's like another sensor input. Okay? And so here I represent it in the cloud as well. Okay? There is uniformity here. That's what I mean. So one of these cluster means go to A. The other one means, oh, this is a rock. The other one means, oh, I'm going forward, and so on. Okay.
How are the one question, like how are the signals being turned into a vector that could be reduced into some dimensionality here? Like all the signals, like go to A seems to be an NLP command or audio signal or something like that, right? How is that turned into a single vector that could be put into the same space?
It's a projection. It's a vector. It's a projection basically. If you have a number, for example, 1, we can project it in a much bigger vector space basically.
I'm asking, like, how do you fuse them into the same space? Do you have a neural network or something that spits out the representation that you cluster, or
Yes. So this is in the notebook that I shared.
Oh, okay.
If you
Okay.
click on the demo link, I just skipped that detail. Okay, it's
Okay.
because I'm trying to explain at the current abstraction level where it's really about data stream. But after how it's done, so sorry, I decided to skip it, and
I'll see them.
but it's inside the notebook. And so, but to answer your question right away, here I'm using a projection, okay? And so I'm using a bit a funky way, just because it's the mathematics I wanted. So I'm using TensorFlow's libraries for embedding. Okay.
Okay.
Okay. And so because this is basically a projection. Okay. And so we have different signals. Some signals are just a simple time series. Some can be more complex. Okay? But all of them, I project them to the same space, and it's the space you can see here. Okay? So I normalize all signals. So if the signal is an image with a 30 by 30 pixels or just a temperature signal over time, these are numbers, and I project them. So it's a matrix multiplication basically on a fixed state, a fixed space, which is here in 3 dimensions.
Yeah. So the matrix is learned or something, is it? Like the projection matrix?
Yes, and that's very important. It's learned. Okay, it means that we try to be data driven and to make as little assumption as possible. Okay.
So is it something like you said you've got 18 servos, so you've got like signals from 18 servos, some temperature and something like that. So your original state vector is probably like 20, 30 dimensional or something like that minimum, right? And you're reducing it to 3 dimensions. So I don't know how like TensorFlow sort of the math works, but is it somewhat equivalent to something like singular values or principal components or something like that? Or is it something more esoteric than that?
So it's not really more esoteric, but it's different because it's let's say I just take the 18 servos positions. So it's an 18 vector, okay? And right now I'm projecting that into a space that is 1024 by 3. So it's actually projected on a plane. Okay, and after that, it's projected again on a 3D space for visualization. So it's hardly more complicated than a single projection. Okay, it's the projection is a core mechanism here. The projection is used for normalizing all signals into a single space, basically.
So I guess you are reducing the 1024 to 3 using some Disney or something. I saw in that graph.
Sorry, there is no reduction here. It's expansion.
No, after the projection, you are for the 3-dimensional viewing. There is a reduction using TSNE or something, just like a non-linear version of PC or something like that, right?
Yes.
Okay.
That's exactly it. Yes. Okay. Yeah. Is that good enough an answer for now, or something's missing here? because it's really the core for most of the rest of the work of what I'm going to talk about after.
Yeah, I think, yeah.
Yeah, it's clear enough for me too. I'll just throw in sort of another sort of bookmark that maybe you can connect up later, like how this connects to what people talk about as latent spaces in deep learning models. So if there's a connection, mention it at some point.
A connection with deep learning?
No, latent spaces in particular in deep learning, because this sort of rhymes vaguely. Yeah, there may be one.
Yes.
Don't let me distract.
No, so no distraction here for me. It's just that so latent space come from statistics, okay, and it's more about things that we can't. It's a state that we can't really
Directly
pin.
observe.
Okay. Yes, directly observe, but that we can also directly pin. Okay. For example, in Bayesian optimization, it's not latent space is not necessarily a number. It can be a random variable. Okay, and so yes, there is. I think there is a parallel with that. Okay, because if we take the robot, let's say the robot is just an assembly of deep learning, deep networks. Okay, that we put together. Okay, and so inside it, there will be latent spaces. Okay. And this is what this is linked to, for example, in this slide, and how we would map the clusters here to labels. Okay. So in that sense, yes, there is a parallel because it's one thing that I still have to answer is how to do that mapping. Okay. And this is a link to AI observability and AI ethics and so on. Okay. But anyway, since this is really about taking data, so data points, and transforming these data points from beginning and as you will see to the end, okay? It's very similar to maybe it's even the same. Okay, I haven't told it this way to latent spaces basically. Okay, so there will be properties on these spaces, and I said that I used a 1024 by 3 matrix to do the first projection. That was not a random state, not a random choice, but pretty arbitrary. Okay, so there are a lot of properties that I'm pretty sure we can identify on such kind of systems. Okay, but to be honest, on this this work, I don't see any. I don't see much innovation or how to say conceptual novelty compared to what we can see in a lot of neural network papers. Okay? Perhaps it's more about the cost into the concept of agency that may be unusual to many, and especially in robotics, because as far as I've seen robots, I don't remember seeing such kind of approach to robots basically. Okay. So sorry I don't think I really answered the question from Venkat whether what is the parallel with latent spaces in deep learning, but it's a very similar in thinking, and I wouldn't be surprised that that at some point it's considered the same basically. It's more about what here is more about what we do with this latent space, what we call it basically.
Yeah, that's what I was looking for. Yeah, that clarifies the parallel.
Okay, thank you. So I will continue, but please do not hesitate to ask questions and so on. Huh? Okay, so we started with raw sensor data, and with some calculation, we project that into a space, and in this space we can see clusters appearing. And what I'm saying is that these clusters are concepts for the robots. Here, for the sake of presentation, I give these concepts, these clusters, I give them labels, okay? But maybe the robot is inventing concepts that are meaningful for it. and none of us is a six-leg robot. Okay, so that's why there are concepts that do not make sense for us. Okay, but still, for the sake of presentation, let's get this mapping. Okay, and so in this project, basically I'm here. The concrete work that has been done so far is here. Okay, and the intention is what follows. Sorry. Yes, is to take these clusters, okay, these concepts, and to start building a small database of evidences. Okay, so that's why I call it evidencing. Okay. And the idea is something that I've talked several times in the past, is that basically our rover has just signals from the sensors, okay, and it's just a soup of data that is shapeless. But with some work, we can start to see some structure in that soup, okay? And out of that soup, can we see some connections, okay? And this is where the notion of rules comes into play, okay? And so this is the evidencing part, okay? And so, for example, the robot had the notion of leg that happens somewhere in the cluster, okay? And the notion of rock, okay? And it can see that it can see just from the raw data. I'm not saying it's correct. It can just observe. It's just finding evidences. We don't know whether they are correct or not. That will be later. Okay, but we can see the concept of log and rock, leg and rock, and that in some cases in the data that leads to being blocked, the state of being blocked, and to damage. Okay. The second one is to say, oh, I'm high, because in fact, it turns out that this spider, you know, by putting all its legs straight, we can the guide can be much higher. Okay, and so it's a concept, okay, of being high, high physically, yeah, and a possible relation to being slow, because in fact, when it's in a high position, it's harder to walk and to walk properly, so to walk fast. On the contrary, to being low leads to being fast. And this is just another soup, but with a bit more structure. Okay, so a lot of things will be discarded by being incorrect or useless at this point in time. And so from all these evidences, this is, okay, so it's getting pretty annoying, sorry, this video. It's about what I'm calling here ruling. Okay, so it's out of the soup of evidences, is to put them together and to find things that that map to each other. Okay, so for example, if several of these candidate rules, candidate evidence show that if you're low, if you're in the low guide, you're going faster, and show that over and over. Okay, step by step, there is this reinforcement. Okay, that imagine your you know, the old AI experiment to have an AI mouse in a maze. Okay, at first the mouse will hit the wall, hit the wall, hit the wall, hit the wall, until at some point it will say that if it hit the wall and randomly turn right, then it can still make progress. Okay, and so it's this feedback. Okay, so hit the wall in the evidencing. If this comes over and over, at some point it will crystallize. Okay, as a rule. And so ruling starts to be more stable. Okay, it's rules that come out of the data. Okay, so it's inside the clusters you can see in the central image. There is yet another structure that is more stable and that has more active meaning. Okay, and so this is where we can say that we can see rules like. For example, the me high becomes means me slow, so it becomes then not just an evidence, but now it's a rule, okay? Something that the robot has learned from its data over time. Okay, the going forward leads to go to A. Okay, so this is an example to. It's a rule, but it's a kind of rule. Is to show that these rules also can disappear over time. Okay, it's a rule that is more local to the mission here. And so this ruling part, maybe it sounds a bit mysterious in my explanation, but the parallel is here clearly with deep learning. Okay, this is what deep learning does. Okay, so you can see evidencing as labels, okay, a data set with labels. You say this image is a cat, and this image is not a cat, and this image is a cat again. Okay? These are soup of a bit structured data. And what deep learning does, supervised learning, okay, is to get this association between an image and a cat, an image and not a cat, and to come up with what is called inductive rule, okay, is to say, okay, I know that if we have such kind of situation, then it's a cat. And if I have this situation, it's not a cat. Okay. So this ruling is what most of deep learning algorithms are doing. Okay. Once we have those rules, they have some stability, something the robot knows in a way. Okay. Then we have the last step in this presentation, in this part. It's something that I call the Tetrising. Okay, so it's the image is Tetris. Okay, is that we have our rules. Okay, and these rules we can just do deduction. Okay, deduction is what we do most of the time. Okay, that we have A gives me B and B gives me C. So A gives me C. Okay, and so this is how by putting the blocks together we line them up properly to find a plan. Okay. For our goal in this case is to go to A. Okay. And so there is, it's really about planning here. So what is traditionally done in advanced robots. But you see, it comes from a much more active, we come up with a plan in a much more active way, much more tightened to the actual data. Okay. Because just remember that from the beginning, we have time series and they're projected as numbers in a matrix, and we compute on this matrix in each of these steps, okay? And so we come up like that with a plan. Okay.
I have a doubt on the evidencing part. Like, where does the initial data, what does it do? Like, is it like a human controlled teleoperated data, or what generates the initial data that trains the matrix or something?
Which matrix? The one that's conceptualizing?
Yeah, the projection matrices are learned, right? So the initial data should be doing something so that these concepts are emerging. Like, is the initial data something that a teleoperated robot is seeing, or is it like a random movements of the robot?
It's a random, well, so that's a very important point because we have to start somewhere. And usually we start at random, okay? And so, and I think it's actually perhaps the only way, but there is a trick here, okay? So we have to keep in mind that the robot has a body, okay, and it has some capabilities. So maybe it has 4 wheels, maybe it has 6 legs, maybe it has 2 legs, okay. And so the matrix, or the cloud of data that the robot will come up with depends on his body by construction. See what I mean?
No, I mean, like in your experiments, the go to A rock going forward, all this has emerged, right? So did you operate the robot for some time and then got these representations from the sensor data? Or I'm just thinking about the origination of the sensor data, which then goes into
Yes.
this step of conceptualizing.
Yes. So sorry, first one clarification. You say what I did. It's not done yet. Okay.
No, okay.
This is what I'm doing. Okay. So
Okay.
it's possible it doesn't work. Okay. But for many reasons, I do have some confidence. Okay. And anyway, on the way to make it. So to answer your question, from the beginning, it's random states. But this is where simulations come into play. Okay.
Okay.
Simulation, especially simulations with accelerated time.
Yeah.
Okay. So I'm working with a simulator where I could easily go to 2,000 times faster than real time,
Hmm.
and it's not converging super fast, but it's making progress. Okay,
Oh, okay.
and so the thing that at the beginning, the spider doesn't know how to walk, and that's
Oh,
right.
okay.
That's good.
Hmm.
I don't want to teach it how to work. I don't want to as a good engineer, assuming I'm a good engineer, of course. Okay, but a good engineer will measure, the position for each servo, and okay, to walk. Okay, I need to lift one leg and wait some time, and after lift the other, and and having the timing right and the angle right. Okay, this is hand coded usually. I'm pretty sure a lot of people here know that it's hand coded. We don't want to do that, and we don't want to do that anymore. So that's why I think starting with a random position is important, because then we make no assumption of the kind of body, and this kind of mechanism could be applied to any kind of body. Okay, but it
Okay.
can learn by itself.
So you reward some exploration or some concept of exploration so that the representations evolve over time or something like.
So there is no notion of reward here.
Okay.
There is no reinforcement learning either, by the way.
Okay. Hmm.
Okay. However, there is something that that comes from cybernetics and that is very, very similar. It's the notion of feedback. Okay. And so the thing that maybe this detail doesn't really matter actually, because it could be cast in terms of reward.
Okay.
It's just that where I'd like to be careful is that the reward is seen as something very utilitarian. Okay. And here, I'm trying to see whether the only utility is what comes from the goal. You can see on the top left of the slide. Okay.
Okay.
What I mean there is that the robot should first learn for itself. Okay. This is what the sensor input comes. Okay. And and so then there is no explicit reward there. There is feedback. Feedback is when when the leg hits the ground, you have feedback from the ground basically. Okay. And so it's similar to the notion of reward, but there is no utility here except if we see the implicit goal of the rover that it needs to survive. So, for example, it needs to find where to charge its batteries. Okay? So I hope I'm not getting too confusing here. It's just that what I'm trying to do here is to reduce the number of assumptions and to reduce the number of things that I have to tell the robot in order to for it to learn. Okay, so the closest image for me is that for me is getting in my head stronger and stronger over time is parenting. Okay, is how you educate a child. Okay, and this is the closest I can see. If but I'm not sure you have any children, but perhaps you have young siblings or cousins. And the thing that when a tiny a baby, okay, you put a bunch of blocks in front of the baby, okay. What is the goal of that? The only goal of that is not to teach mathematics right away and or to teach architecture. Okay, it's for the baby to experience grabbing, to experience moving, to experience colors, to experience shapes, to experience dexterity of the. It's about all that, and you see. There is no goal except that. Okay.
Yeah, that's why I asked whether it's like a novelty or something. Like you're just seeking novel experiences, like more of an exploratory kind of a reward. If we even call it a reward, it's more like you're rewarding exploration more than anything else.
So yes, we can cast it that way. Okay. So there is one thing, but you have to be careful here with that. It's correct. To my view, it's correct. Huh? However, sorry. It's still a coached exploration. Okay, the coach is very important here. Okay, in the sense that again, the baby, if you put blocks in front of the baby doesn't have to focus on those blocks. If the baby is not interested, it will do something else. Okay. So what I mean by here by that, it's you use the word novelty. Okay. Here it's not really novelty. Okay. It's coached. Okay. There is still environment on which we'd like it to focus, which we'd like the robot to focus. Okay. And by the way, I hope I don't hurt any feeling by comparing a robot to a baby and a baby to a robot. It's not grand novelty here. Okay. It's more about building inside the robot the capability to take into account at some point in the future novelty. Okay, so it's very critical. Okay, that here the data from the sensor input. In the experiences so far, the data is a small data set. We have something like 1,000 data points and so on over 18 sensors. Okay, and so what you can see here is just a result of that. Okay. But if we continue sending data and feeding the data into the cloud, I'm pretty sure the cloud will change shape. Okay, some stable concepts will stay, but over time, some concepts will just merge with others, or maybe will most likely divide. Will be refined and stuff like that. Okay, and so I hope with such kind of mechanisms to give the robot the capability to find the novelty over time at some point, but not right now.
Okay, I think all my questions were just to get a clarity for myself on how the projection matrices change over time. What is the signal that is making the projection matrix update itself or something? That's
it's how the projection is done is fixed. Okay.
Okay, so it's just random projections. That's it, and you get the representations and then cluster them over time.
Right now, yes, it's done like that. But the thing that is continuous projection is that, it's about digitization. Okay, so the robot is reading data at a fixed pace. Okay, and so for each data point, it's projected, but it can also reflect. It can reflect. Right now, it's not done, but it can update the projection as well.
Okay. Yeah, makes sense.
Okay, so I'm continuing for now. Okay, so briefly to be back on track. So we have here on this image, on the top left, we have sensor inputs and another input called the goal. Okay, the command. Okay, all that is fed to the algorithm that normalize all that data from different kind of sensors to a fixed space. Okay. And by doing that, we can see, okay, that some clusters happen in this case, okay, but I think it's pretty generic in a way because I'm doing no special treatment here. And so we have these clusters. These clusters are just concepts that are meaningful for the robots. This is the conceptualization part. And these concepts, we have another mechanism which I call evidencing that take them and make a candidate rules out of them. So it's a big soup of candidate rules. The next step is ruling, where we take this soup of rules and we try to find the ones that come over and over, and we find the one that remain, okay, and they reinforce themselves there. And so what remains are rules. Okay? And using these rules, the last step is the Tetrising, okay, where we have a goal, okay, and we'd like to achieve it. Okay, it's an end goal. And so how can we use the rules and put them together to make a chain of actions toward the goal? Okay. And so once we have the goal, okay, so that's the last point at the bottom left of the image, we have the command step, okay, that we take an action in the environment. And this is another signal that we apply to the environment. Here, it means to apply a signal to the servos for the legs. Okay. And so all this is just one tick. Okay. So if you imagine that your robot, reading the input, doing something and doing an action, all the time I took to explain that, I'm sorry, it's one tick. Okay. And so it does that over and over and over. Okay. So again, if we look at it from what's really happening in the head of the robot, it's something like that. Okay, it's to take the time series data, and we project that on a space that gives us some clusters. These clusters are transformed into another cluster for where we can see evidences, transformed again in another cluster, okay, for ruling, and again in a plan, okay, which is at the end of the day applied at the end of the loop, sorry, applied to the motors. And so you see, what is a bit hard to explain, a bit perhaps mysterious, is that where is the programming there? Okay, but everything is based on programming here, or taking sensor data. It's about what program we write to take this sensor data and turn it into another kind of sensor data that we call actuator actions, basically.
Can you say something about how you use feedback from applying this in order to fine-tune the process?
So here the feedback is implicit and insufficient. Okay, size question showed most of it. Okay, because the thing is that at the conceptualizing stage, okay, I've said that it's mainly about the projection and passing forward the projected data. Okay, it's normalized and more usable. But feedback happens here. Okay, is that for each new data input, we pass it through the concepts known today at this point in time to make some decisions. But at the same time, it's a new data point we can put in the cluster. Okay, so this is where, and putting the data in the cluster will affect the clusters. Okay? And so this is one part of the feedback. Another feedback is well, no, sorry, that's the central mechanism, because this will trickle down into new evidences. And new evidences may trigger new rules or may trigger nothing if we are just accumulating new evidences. And at the end of the day, should affect the plan that is running at this point. So here, feedback happens in actually a pretty feed-forward fashion, if you see what I mean.
So it's not feedback. I'm asking when you finish the process and you apply the commands that you learned from tetrizing,
yep,
how do you use that to fine-tune what you did before?
So that's when we have a new data point coming in from the input. So let's start backward. Okay, we make an action in the environment. So the bottom left is an action that has been taken on the servos. Okay, this action will trigger some new input next. Okay, so we go back to the input that will create a new data point in the conceptualization space. Okay. And so that data point is projected in the space and maybe used later. Okay, but okay, it's about the timing. Okay, that when the new data point comes into the existing clusters, okay, it's used at that point to create the rest. But here also, the pointer can be also integrated into the cluster, into the clusters. Okay, and that integration will update the clusters. This is where the feedback happens, and I'm saying it's also feed forward because it's in the process of using that data point as well.
I'll explain what bothers me. When you have an existing cluster with 1,000 points in it, and you add one more point, it doesn't make a lot of change. But when we
which is good.
I'm sorry?
Which is very good.
But on the other hand, if I actually generated a command and the command doesn't work, it's more meaningful than just a data point that came in because I was doing something else. It tells me something about the entire process of tetrizing and ruling and evidencing. That
So
seems strange.
so the thing that it's I would say, imagine you are trying to push a wall, okay?
Mhm.
And so the action is to with the hand on the wall. At first, we're more likely not to push very strongly, okay? And if we don't push very strongly on the wall, we won't have a very strong feedback, okay? It means what our touch sensors will read from that is some signal, okay, but not very significant at first. If it's when we really push stronger that we see, oh yeah, I'm not going to be able to push, okay, and then that becomes maybe more conscious to say, okay, now I have a strong signal. So far I have ignored small signals that says, okay, I'm touching something, okay, but at some point, because of the level of signal that came, some point we pass a threshold and boom, I have the consciousness of, yeah, I'm not going to be able to push that wall, okay. So of course, I'm assuming here you're just pushing with the hand and you're not using other. If you see the wall, you already know it, okay? But I'm simplifying the problem to just pushing with one hand. Okay. So small signals are still useful, I believe.
Can you
What is
explain
very
how
important is
the sorry.
Oh, sorry. Just a last one is that what is very important is to see signals over time, okay? Because they accumulate, okay? This is why such kind of representation to me is interesting, is because, you know, a cluster at first, maybe we can have just a few points, but as similar points come in, it becomes a bigger cluster, it becomes more meaningful, okay? That's the kind of idea, okay? It's a, you know, I consider our body and, you know, because of a DNA, because of evolution, such kind of explanations, we actually know quite a lot from when we are born, basically. Okay, just because of that. And so, one problem of a lot of AI is that we ignore that, okay? And that is actually a strength we have deep learning, and you know, it has been called System 1 at some point for that reason. It's deep learning goes deeper into perception, okay, into linking to lower level signals. Okay? Sorry.
So how do you map? Is the ruling and tetrizing also like automatic steps, or is there any goal involved there? Like, is it like coded to do some? No, I can't wrap around how that happens. Like, how does that generate the actuator signals? Like,
Okay, so imagine you have a tube, okay, a long tube, you know, like a hose, okay.
Okay.
If you put water in on one side of the hose, okay, what do you get at the other end?
Water.
Yes, water. Here it's the same image. That at some here from the sensors, okay, and you have to be. There is one thing here that sensor and actuators are actually the same thing. A sensor is an actuator. Oh no, an actuator is a sensor actually. Okay, this is how it's taught, by the way, at the university. Okay, so here we have a sensor input like water. Okay, it goes through the tube. Okay, and at the exit we get what? Again, water. The difference is that the water has changed a little bit. If we look at the position of water atoms in the water fluid, they are not at the same position, and it's about what's happening here. Okay.
Yeah, I'm just thinking about, like, in general thing. I think you'll write a mapping of what to do in some representation of the sensor happens. You do this or something. Here, are you just projecting again using some matrix to just project it back to actuator space or something, like from tetrizing? Like,
Yes.
okay.
So basically, what I'm trying to achieve here is, you know, in traditional robotics, we have things like perception, planning, actuation, such kind of categories. So what I'm trying here is to define each of them as a data transformation stage.
Okay.
Okay.
Yeah.
And so, and to be honest, it was in my head for a long time, but it's since I'm working on this project that it's become clear what I really want to do. And recently I see that it's actually becoming more common. That's where, I think Venkat shared the software 2.0 point of view. And one of my friends shared with me something I shared called Autonomy 2.0 from Lyft. Okay. They are focusing on self-driving, but a rover is kind of self-driving car. Okay. And so there are differences, I think, still, but I think there is convergence too. I think there is stronger signal on such kind of ideas. And it looks like they are doing something very similar, if not actually the same, and with very strong people around, okay, where they are redefining everything in terms of data transformation from end to end. And as your previous question, when I talked about parenting and education, this is where the software tool from what the name? It's not Kaspersky, it's Karpathy.
No,
okay.
Yeah, Karpathy. Yeah.
Yes.
Yeah.
Where he wrote something, or he said something about like right now it's about writing code, but in the future it should be software 2 is about choosing data sets basically. Okay.
Yeah.
That's parenting in a way, because we choose the data we give to the algorithm, and we let the algorithm learn for itself. Okay. Like parenting in many ways. So to answer your question, yes, ruling and tetralizing as well will be some form of data transformation, and I'm not there yet. Sorry.
Okay.
I do have some ideas.
So you see them as a what is it? In general, if you take some RL or something, they just put the sensor data into some neural net and it spits out either a value function or directly the policy actions or something. But here it seems like you have divided into 4 steps, which might be more interpretable or something. But
yes,
it's not. But it's not like and in RL you just put the sensor data in and it spits out the action. Here we are like remembering the latent space or the vectors and then using them to form the decision making. From what I could understand, I'm just summarizing what I understood.
Sorry, I could not understand everything, but it sounds so. Yes. Okay. Yeah, and so the breakdown in four stages is more kind of transition between there is direct mapping with what is done in traditional robotics. Okay. I mentioned perception. So perception is basically the top row. Okay. We have perception, planning, and perception, to put it simply. Okay. And planning is testing, tracing. Yeah. Okay. There is some mapping. Okay. And so it's more about how to structure the presentation here. Okay. Right now I'm, I have kind of a plan. Okay. And trying to iterate on that plan. But the thing is that what it will really be, I don't know. And I'm pretty sure there will be optimizations. I'm not sure it's the right word. Okay. But there will be ways that we will discover over time to make that to a different mapping that will be more that will have more sense then, basically. Okay. Right now, I hope this decomposition kind of makes sense, okay, because it's somewhat close to what is done in robotics usually. But at the same time, you see, I'm choosing perhaps weird words that look weird on purpose to show that I'd like to be talking about it from a different standpoint, basically. Is it good? Yeah. I propose to go forward because it's already an hour and 15 minutes. Yeah. Yes. So this slide, I presented that in August, and it's to show the continuity between what I was talking then and talking now, because I've changed a bit the terminology. Okay. And so this image meant we have the sensor at the top, and it's a data soup, and we digitize this. It's what I call conceptualize now. Okay, and from this conceptualization, we do things like abduction, induction, and reduction. Okay. I will pass on the detail why it's structured this way, but there is a meaning here. Okay, why it's done this way. The reason is that abduction, so the evidencing now, it's a big soup. This is where we try to find evidences, and usually after it's the work of induction to create rules, and after once you have the rules, we have the deductive parts. Okay, and they get closer to the sensors in this image because when we're in a state when we have deductive rules, they are pretty stable inside us. So it means we can react much faster. Okay. The deduction is if you have A, B, and B, C, you have AC directly. Okay. So it's a very close feedback with the sensor. Okay. So you can take action. It's like a reflex basically. While induction and abduction require longer reasoning, require more data and more time to perform. Okay. So today the image hasn't changed, it's still the plan. Okay, the focus was on the layer I mentioned, and my next step will be at the bottom layer, which is about abductive reasoning, and I hope to be able to demonstrate a bit more fun stuff then. Okay. I have some discussion points, but we've touched several of these points. I propose to pass on this right now and come back depending on our group motivation. Okay, but I think anyway that's the end. Okay, so okay, sorry, just about discussion. I had a discussion about how this is really related to what we're doing. Okay, because that may sound abstract and so on, but it's really about having autonomous robots, more autonomous robots. Okay, and it's pretty critical in space. Okay, because we know that once we have a rover on Mars. If the rover is blocked by a tiny rock in front of it, that's a big issue. Okay. Also, a bit the second bullet point here is that it's how relevant this could be compared to others, and especially to what Tesla and Lyft are talking about right now. Well, it seems pretty relevant, I believe. Okay, with quite some potential. And recently we talked about maybe the value of doing an operating system. And to me, that should be core, or such kind of things should be core to such kind of operating system. And so the last point is it's a citation from a researcher that I like very much. So he's been on similar topics for a pretty long time. Okay, he's more into biology, which is pretty consistent with a lot of things I've talked about today. And I won't read it now, but it's pretty interesting how he defines what a minimal autonomous agent is. Okay, there's something that we could discuss at some point, because at the end of the day, we would like our rovers to be pretty useful. Okay, and so autonomy becomes pretty interesting then. Okay, so I'm ending the presentation here, but would be delighted to discuss any of these matters or any of your questions.
Is there a representation of time anywhere in this? Like, say the state seems to be every sensor step is independently encoded into the space, right? What about conditioning across like the previous state and the next state? Like, yeah, in the conceptualizing space.
Mm-hmm. So yes, so so there is something that I haven't talked about here. I'm slicing the time series. Okay, that it can work if I take only one reading at a time. Okay, but the thing that is not super interesting, and I think that indicates that it's not enough. So what I'm doing now is I'm taking a slice. Okay, I'm taking the history of the 10 last readings, and I project. I project all that into space. Okay, so you're pointing out something very important, because it's a kind of I still have a very parametric ways of doing it, okay? And how did I choose my parameter? I don't remember. Maybe I take the last 10 readings or something like that. It's in the notebook. Huh?
Okay.
So
Yeah, I'll
how
see
do I
them.
choose that? Yeah.
Mm.
So yes, it's arbitrary. But we have to keep in mind that, you know, when we study, for example, biological brains, they are very similar kind of numbers, okay? And so in the old days, there was this a paper that was trying to be funny about it, saying that memory buffers in the brain are about 7 units. I don't remember what the unit is. It's a 7 units plus minus 2. Okay, so for a long time, that was 7 units plus minus 2. Okay? And so this is how the biology is designed. Okay, that there is a bandwidth in our biological neural network. Okay, so what is the ideal number for that? I can't say, okay, but it's I'm trying to have as few parameters as possible, and this is one of them. But at the same time, this one I'm not trying to get rid of it just because of this old paper. I think I found it through a researcher called Herbert Simon, so a Nobel Prize, I think in economy or something like that, a long time ago. Okay. But you're right. There is something about looking into the duration.
Would something like RNN or something help there? Even if it's randomly initialized, the projections might have some dependencies between the states. Because I have seen some interesting work where even a randomly initialized RNN can spit out some representations that are useful when you're doing deep learning. Like people take a randomly initialized RNN and inputted some data and get the final representation, and then they just learn a linear network to do some task on it, but they don't update the RNN. So it's just acts as a projection layer, but still it can do some interdependencies over time or something. I'm not yeah.
So I can't tell you for sure, but that's possible. Okay. For me, one of the reasons not to use RNN kind of algorithms is because they are very expensive. Okay, very expensive and very slow to learn. If you see what I've done in the notebook, I mean, it's very about a mathematical projection. I'm using TensorFlow to do that, but basically I'm reusing the mathematical operation more than the name of the layer.
Yeah.
And I'm trying to be careful because, you know, some of these implementation in TensorFlow, they're optimized for an intended use. Okay, so I'm trying to be careful that it does what I hope it to do. Okay, but back to RNN, they are costly. Okay, and we don't have much data yet. Okay, that is what also is a bit exciting and convincing that thanks to Meyer and maybe at some point to the whole group, we should be able to collect significant amount of data where such kind of approach or other kind of approaches, you know, we could leverage and test and do things basically. Okay. So RNN usually are more greedy in terms of data, and here I just don't have it. But they're also to me they're a bit overkill. Okay, they're overkill,
I mean,
and again, here I'm trying, you know, to have as little assumption as possible on the structure of what is needed and what's going on.
Okay.
The RNNs, they are already making a lot of assumptions about many things.
Okay. Yeah. Okay.
Conceptually, I think it should work. Okay, and potentially bring even some values. I just don't know. I didn't look at it. Sorry, I was more talking about why I did not choose them in the first place.
Can you guess perhaps how a rover which is self-programmed will look different on the outside from a rover that was hand-programmed? Do you think
okay,
there's a difference between them?
so that's very interesting because that links to a very concrete problem, which is in engineering, which is safety. Okay, because with such kind of approach, it's very possible that, let's say the spider boat learns to walk in a very strange way. Okay, but from its point of view, it will be efficient, and maybe it is, and we need some time to understand why. But perhaps it will do. I don't know. It will, maybe the front legs will be thrown forward, to give a, because let's say that I train my spider boat in my office where everything's slippery basically. Okay, and maybe the robot will learn that by doing that, it will slide forward and achieve its goal of walking forward much faster, much more efficiently, saving a lot of energy. Okay, it's very possible. Okay, I hope actually to find that because that will first a lot of fun, but also that would show some potential for creativity somewhere. Okay, so I think such kind of approach that is more raw data driven have this potential and difference with a traditional way of building a robot, because building a robot, basically we have some beliefs about what an efficient move is, and a lot of these beliefs are driven by knowledge about physics and so on. Okay, is that if we lift a leg, we will try to lift it as little as possible to avoid spending too much energy. So when we code it, we will try to do that. Okay, and if we write by hand, we write version 1, and we have some telemetry from it. Version 2, from the telemetry, we will sign, okay, I can do my move even better by reducing the amount of lift on the legs, and I can save more energy. Okay, but proceeding this way, we are doing something very anthropomorphic and also science-driven. Okay, but science-driven based on analogy with what we know in physics and stuff like that. Okay? So in that sense, I think this has the potential, but also the risk to create very different results than what we would code by hand.
All right. Are we ready to wrap for today? Yeah. So next week, I believe, Sai, it's your